Thank you.
We're a little bit running on behind the schedule, so we're going to move on quickly. So the next two speakers, one is me, the other one is my boss. So myself is, I'm Chester Chen. I'm the Senior Product Manager and Engineering Manager at NVIDIA Federal Learning Framework called NVIDIA FLARE. So that's where the address, the Rhino using the library to build on. Peter is the Director of Engineering in charge of both the Federal Learning Engineering and the research. So I'm going to do the first part of the introduction about what the NVIDIA FLARE is about, give you a quick review, and some of the stuff which Tricia already covered, I'm going pretty quickly, but I'm mostly focusing a little bit of highlights of the FLARE features, and then go through the use cases, where it has been used, and then I'll skip the part Tricia already covered, and then the second part, Peter is going to talk about more detail in terms of deployment, scalabilities, and our future roadmaps. Thank you. So this part you already know, right? So this is what is the federal learning. So essentially, you basically don't move the data, you move the model. The model send it over to all the sites, whether it's the banks or hospitals, and then you do the local training. You only share the model with this central aggregator or coordinator, and then do some kind of a weighted averaging and send it back. This is one of the typical Fed averaging type of algorithms, but there are many others. There's a cyclic, like a round robin type. There's a swarm learning, means you don't use the central server to aggregate. So you can send the aggregation at each client randomly at each round. So there's many different ways, and of course we do this because of the privacy regulation. Sometimes it's purely economics. So the FLARE is an open source Apache 2 open source library. So basically you can use it for any way you want in production. So we designed for production. Actually, the whole FLARE was created working with the Rhino's founder during the COVID time, try to predict the oxygen usage, which patient I should have gave the oxygen machine to. So we connected, around the world, 20 hospitals together. So we created a FLARE. That's where FLARE was first born, and since then we've been open source. So there's a lot of technologies Tricia already covered, how to addressing the privacies and some of the differential privacy, adding noises to the model during the transfer. Homomorphic encryption means you're averaging in the encrypted space. But nobody can see it, but it's an encrypted space, but the actual results coming out of it is the same. Computational computing basically is a hardware-based, rooted in all the trust, the root of trust in the hardware, in the GPUs and CPUs, and then it goes all the way up. FLARE itself is model or a framework agnostic. So basically we support any frameworks, whether it's a PyTorch, Lightning, XGBoost, scikit-learn, TensorFlow, we support them all. And it doesn't really matter, it's a financial model or it's a image, like a medical imaging, other models. We have simple APIs, I will show you a little bit more. And there's a whole end-to-end life cycle, essentially from simulation, deployment, all the way to large-scale productions. So we support on-prem, and Peter will talk more on that, and of course, federated compute. So here is one little example, say how simple the API could be. So the left side is an API for PyTorch Lightning training. So these code are directly copied from the Lightning examples. It's basically CFAR 10, you do the training, few lines of code. You say, okay, so I don't know anything about federal learning. How do I turn that into a federal learning training code? So you see this highlighted areas, essentially, including the import is the 5 lines of code changes. That turn to that standard PyTorch training code into federated the client training code. So, and you say, okay, great, I got the training code, but how do I, you talk about the federal averaging, what kind of averaging I'm using? So there's a different type of averaging algorithms that we decided to build them into recipes. So there's a bunch of recipes. So this is the one recipe for Fed average recipe. So essentially you specify how many clients you want, how many minimum number of clients you want, and what type of models, and then your put the training script, which is the code you just converted with the 4 lines, and then you put it on simulation, you can run. Of course, the simulation environment can be changed into production environment, or with something we call a POC, which is a simulation the production locally in your home machines. So local machines. So there's a bunch of recipes already available. We released on 2.8, and so you can see that there's all kind of recipes. As I mentioned, that we're model agnostic, whether it's large language models and all that stuff we support. We support, like if you do a biologies or medical imaging, MONAI, BioNeMOs, graph, we can do all that kind of things. And there's a lot of the different workflow I mentioned. Federated averaging, almost like a scatter-gather type of thing, but it also have a swarm learning, cyclic, I mentioned already. There's also something called a horizontal federated learning. So basically means all the features are around different clients the same. And there's other places are vertical, means that a different feature have a different features. And then you have to assemble the data sets alignment, align them together. So you can also do split learning, means that you can take a different layer of the models and say, hey, this layer training on the server, the other layer on the client, or simply this client trained this part of the layer, the other trained the other. So you can do all kind of things. And Adrish already showed some of the ML flow related stuff. We can have ML flow with some biases, TensorFlow. I think he showed a TensorFlow. We also support with some biases and ML flow. So essentially, those are things you can directly use. You can stream the losses to the server, or you choose not to. So I think right now maybe to do slightly differently, but you can have all these options you have. Of course, you can not just do the training, you can do evaluations you send a model to evaluate it on the different data, do the model evaluation. And we also have something called a cross-site evaluation. Basically, you send a different size, different sites, the clients send to the other clients to see the cross site evaluate whether how good it is. Of course, as Josh emphasized already, so there's more than just a training. So this is kind of a federated computer. You can do the data discovery. So you say what data you have, or harmonizations, and basically and then quality control. See, I have the data, and is the quality good enough? You do this auto distribution, filtering before you even put them in the participation. The data need to be standardized and need to augmented, and you do this federated ETL for harmonizations. And then you do the analytics and do federated statistics and all the other quantile, histograms, various standard variations, all the other stuff can be calculated. Finally, you get this agentic workflow. So, of course, since we start with production, so basically we very emphasize on the enterprise security. So there's a lot of security stuff we put it in. We support both the the standard TLS or mutual TLS, whether we also recently reduced to a single port as address has been used. And then a lot of stuff is PKI based. Everything's you have a RBAC, essentially role access control, very fine grain access permissions. On the other side, so because all the different sites usually is institutions, hospitals, financials, and all the other places. So they also have their own controls in terms of what user can or cannot do. So we have this site-specific authorizations allow you to put a different security and privacy policies around them. Recently, on our last release, we're also adding something called a study scoped dataset isolation. So in other words, if you on the same platform, you decided to have, say, 8 studies, in parallel, how do you avoid these studies access to the other access code? So we basically isolate them based on the study. The user access to one study may not be access to the other study. So the data sets is, if you're using Docker or Kubernetes, the volume itself is isolated. You cannot physically access them. Adresh is already talking about the differential privacy. I'm not going to talk too much of this. Okay, confidential computing. So I drove down a little bit on this. So one part of the confidential computing is building the trust from the hardware. So there's the user usually has a lot of concerns. Okay, so if I'm the model owner, I probably want to worry my model being leaked out if I send a model to the other training. So if I don't want to share the model for everyone. But if I'm the data owner, I probably also want to say, hey, if you do some compute on my node, I don't want my data leaked out. So how do I solve this kind of a conflict requirements? So computational computing is kind of offer one of the approaches. So, but if you think about a federated learning, so it's more than just one computer. So there's a client and server. So basically one part of it is basically secure. How do we secure the server side? Essentially, I send a model out to the server. The model is some smart engineer decided to, okay, I can reverse engineer this model to get the privacy data. So that's where the privacy enhancing technologies come in and say, hey, why don't you add noises? Why don't you encrypt it in the encrypted space? And both have these merits, but both have these drawbacks. In certain cases, you cannot use the other. Because you're adding noises, your accuracy may go down. You add homomorphic encryptions because you turn the bits into very, very long. So all of a sudden, your compute cost is very, very long. So basically, it takes a long time. So computational computing is another alternative. It basically means, what if you're using computational computing to lock down the server, nobody can access, including yourself? So in that case, you can do this, aggregation inside this so-called trust execution environment, TEE, inside the TEE, so nobody can access to, so that you essentially achieve the secure aggregation. But you can also use computational computing on the client nodes. So basically, that's where the model IP protection comes in. Suppose I have a model, I send it over to the other side, but even though I work with you, but I don't really trust you. So I'm afraid that you're going to tamper my model, or simply add a one line of code to say, copy this model I received, save to my disk, my model is gone, right? So basically, how do I avoid to do that? So if you do this in the computational computing on the client side, essentially lock down that kind of node. You build the computational VM in such a way, if you tamper one bit, the whole attestation, there's a concept called attestation, essentially verify something has been tampered from the hardware to all the way to the software. The attestation will fail. So if it is a fail, the whole disk is not, able to decrypt. So the model will not send it over. So there's a whole, FLARE has already integrated this into for computational VM. So, okay, so this is the part I want to show you, say, okay, we talk about the technology, talk quite a bit. So, who has been used them in the real world? FLARE has been used for quite a number of places. The majority of them using healthcare and life science, particularly in cancer research, drug discovery, and in some cases for near future cares, needs prediction, clinical trial operation. So, but the majority focus on the cancer and the drug discoveries. And the next category is the financial services, mostly focus on anti-money laundries or fraud detections. The next one is, I just blandly call it scientific computing or national securities, essentially because of the mostly focus on the either the weather predictions and that sort of things, or the national government, like for example DOE. I'll show you in a second. And the next category is the transportation, like for example, mostly focus on self-driving cars. And it could be self-driving car data across data centers or self-driving cars in car itself. So this one, Tricia already covered. So I'm just going to skip this. This one, Tricia also covered. I'm going to talk maybe one more sentence on this. So Eli Lilly is, as you know, is a big pharma companies, and then they have already in the first, they said they have already built a bunch of models, like 16 different models. They claim about $1 million worth of models, and they said, okay, I have these models. How do I make them get better? I don't have any more data. So these AI models are, really based on their own internal, carefully curated data. So it's a really high quality data. So the model is really good, but they don't have other variety of data to get it better. So they decided to start this company subsidiary called the Cnudde. Cnudde purpose is essentially using other web lab or startups data to fine tune this model. So in exchange, they decided to say, I'll give this model for you to free, but you need to help me to use this model to train, so I can refine this model. So that's where this Cnudde comes in. Initially, it's about, I forgot, it's a dozen of these startups. Now it's over 100. So so the rhinos runs on this. So there's okay. So because I quickly adding two more cases. I saw Adrian already showed the two cases that we're going to talk about it. So this is another use case is from Roche. Roche is also using FLARE to do this, medical imaging, and of course they also do the pharma side as well. But in this particular cases, it's there's like several hospitals in Zurich, hospital in the University of Zurich and in the USZ and actually and across a couple of countries. And then they mostly do this, lesion segmentations using different sites. The other cases in which Drescher didn't mention, as I quickly add this to this another project called Fate. Fate is a 5 pharma companies get together. These AbbVie, Amgen, AstraZeneca, Johnson & Johnson, and UCB, and so they get together. So their goals essentially is to try to predict certain chemical properties, like for example, like a biophysical properties of viscosity, aggregation, stability, liability, that sort of things. They want to see, how, because none of them have enough data to do that themselves. So even though they're probably commercial competitors, but also they decided to band together to do this federation. Okay, so financial services, this is kind of one example on there are our recent studies. We have others, but I just want to, this is more recently, JP Morgan Bank in New York, Royal Bank of Canada, and plus the Deep Temple is the startup on the, cybersecurity part, and then decided to get together with the NVIDIA's. So we provide the infrastructure, so they run the 5 different cases, and then they publish a paper. So this is the last year GTC, Washington, D.C., they were talking, have a panel discussion on this. So another case is not financial services, but it's kind of a sovereign AI cases. Taiwan government, they have, the Taiwan government, like a Ministry of Health and Welfare, and they decided to connect all the hospital together in this case, in 4 medical center, initially with the 16 hospitals, to do so-called external clinical validation. So it means that if one hospital, one medical center decided to say, hey, I got an AI model, I can cure cancer, does that even apply to the other hospitals? So they want to, and even they want a FDA approval, so Taiwan have an equivalent in TFDA, so that if the Taiwan TFDA approval for usage, they have to go through this validation before they actually get the approval. So this is kind of an inaugural picture they had, with the 16 hospitals and RVP here in this event. So and then later on, the minister of the Taiwan Minister of Welfare, and in the TV interview said that in 5 years they're going to be expand the hospital into 450 hospitals.
So where the GPUs are running in the government data center?
Well, sure. Sorry. Well, in Taiwan, the hospital. Oh, sorry. I'm going the wrong direction. Sorry. Oh, sorry. Where was it? What I did? Into the wrong direction. So the GPUs, the GPUs are hospitals, but the government also has a GPU on the AI center themselves. Yeah. For federal learning, frankly, the GPU should be on the edge on the hospital, but they have both. So the government has they purchase an AI center for other purposes as well as the federal learning. Okay, so let's go quickly. Sorry. I'm probably running too much time already. So this is another government cases. The Department of Energy, basically we have several cases. The Department of Energy National Lab using NVIDIA FLARE. This is one of those. So in this case, 3 national labs decide to collaborating together to train large language models for their classified material, their secret things. So in this case, is 3 labs: Sandia National Labs, Sandia Labs, Lawrence Livermore, and Los Altos. So 3 of them decided to train a model. So they actually, at the first page, and then they train the model. They even name the models called called a Chandler, which happened to be the middle place of the city, between the 3 labs. And so they decided to choose that. So they're continue to train the bigger models, and this is based on their published articles. Okay, so there's the next one is our self-driving car is actually NVIDIA's own use cases. So this is already in production 2-3 years. So essentially, when they train the self-driving car models, and the model in training in one country, for example, US, cannot be applied for China because it doesn't work that well. So one way is to move data together. Of course, China doesn't allow the data come out of the country. So they decided to using federated learning. So in this case, they're using cyclic, not the Fed average, they're using cyclic, kind of round robin around two countries. So they didn't have a lot of clients essentially, but essentially two cancer centers, and the coordinator in the server is in Japan. And then they set another one in Hong Kong for development. So in this case, but they have go through many rounds, and as I said, it's like the in production for several years, and they already produce a dozen of these different models, and for whether it's parking, sensing, and all the other things. I think I gave you a good flavor of all different cases, and I'll turn to Peter to explain more about the other pieces.
Thanks, Chester. Okay, maybe I'll skip some slides too. I don't have too many slides, but I want to talk about some of the more details. So, we'll see. So first thing is about deployment. And one thing that kind of we deploy in very different kind of cases. The national labs deploy on really supercomputers, 2000 node computers, typically learn using Slurm or other kind of HPC things. So that's the one extreme. And the other extreme is maybe some small regional hospital that has one server somewhere on a desk somewhere, right? And that extreme makes it kind of interesting. So when we launch jobs, we talked about these both at the server and at the clients, we traditionally just launch it in a new process. But there's a lot of problems with that for security reasons and so on. And so in our recent release, we really focused a lot on deployment and around both Docker and Kubernetes. So you can now run, both, in traditionally just on a VM, you can run in Docker, you can run in Kubernetes with the advantage of the full auto scaling of Kubernetes. We can run in Slurm already, but in future releases, we will improve Slurm capabilities. So from a Flare open source point of view, no matter which environment you prefer, we will make sure it's supported and with full security and isolation. So for us, we work with a whole range of partners, and security is really central. One of the problems if you run these different jobs, obviously, is that not only do they use resources, they can also interfere with each other. So one job could run, if you don't isolate them well, one will run out of memory, and then everything else might crash. So that is not a good idea. Also, we want the data to be totally separate. So I think there's two different ways we can run code. I think that wasn't really mentioned so far, is we can allow random code from I'll go back a slide. If the person running the job, you could, in principle, we allow it, it's a setting, can run random Python code or any code really at the clients. And that obviously is, in that case, Flare, its main job is in fact remote execution, right? That's the whole idea. And in some settings that works. And in other settings, it is not allowed, and all the code that gets executed gets pre-approved, which is obviously safer. From a Flare perspective, we want to allow both. And even if you have random compute that is running, we still want this to be totally secure. So even if this is random code executed, we want this to run in a container with very constrained access to its data so that it should still be safe. If you don't like that, then you can disable it, and then we won't do it. So Flare, as an open source layer, wants to provide a very broad technology and very broad capability while guaranteeing the security. So we have in our latest release native Kubernetes, native Docker, and future we will have better things for any of the main systems. And obviously this runs in all of the clouds without problems. I'll talk a bit about agents. Agents obviously are key. Like we use them extensively as we write the code ourselves for all kind of purposes. We're very strong proponents of using coding agents, and we use them heavily. But we also see that with Flare, we wanted to make it very, very easy for agents to deal with Flare, so that we bring the adoption, the barrier to adoption as low as possible. So with 2.8, we redid, for example, our CLIs with a specific purpose to make them easy for coding agents to use. I'm going to go one slide. I'll skip that slide. So this is a very interesting work. So at NVIDIA, we do both development of open source code, and we do research around federated learning. So we have a research team that collaborates with a whole range of universities around federated learning algorithms, differential privacy, all these different aspects. A lot of them are not really solved yet because there's a fundamental conflict that we have here that is not resolvable in some kind of way, right? Our goal is we want to learn from all the data in these different sites. The only way to learn is to share information, right? Information gets shared. At the same time, the people who have it don't want private information, for example, to be shared. So there's this tension that is not easily resolvable and is not perfectly resolved. So these algorithms, like differential privacy, it's all about trade-offs. So we do a lot of research. And we have, in our latest release, and we're going to productize it, started to use AI agents for improving our algorithms and our research. So we have, there's a blog, a developer blog, where we now can run fully autonomously for tests and agent runs that run for many, many days or weeks. And they will go, like in this example, have a particular algorithm and try to optimize accuracy. And you don't have to be an expert in federated learning if you're, normal data scientist. You, in fact, have to do really nothing. You just say, here's the algorithm, here's the data, go try to optimize it. And as it improves over time, it just tries to optimize, it changes the code, runs the code, and improves, and then does literature research along the way and on federated learning algorithms. So all these different recipes and variants, and there's so many things to tweak as a data scientist. And agents are just really, really good at it. It's probably not as good as the best expert in doing this thing, but it's certainly way better than most people. And so we ran it on a federated learning benchmark, and the green ones is what the agent did, and the gray ones is the reference number that is published. So in almost all applications, just running the agents on the system for a while improves what is published. I'm not sure that what is published is the best that's possible, achievable, but you don't really have to have a large research team. You can use the agents to improve. And so we have real gains that really help. And this, again, lowers the barrier of entry significantly. One other thing and so agents is central in also our future work. But I want to talk about one other thing that isn't, that's kind of some cool thing we recently released, is the scaling of the model. So as models become bigger and larger models become more popular, scaling of them becomes a challenge. So in our latest release, we added a feature to, in the server, you need to aggregate all this data, right? And traditionally, we aggregate it in memory. And this means that because all these different clients are sending this data at the same time, it uses quite a bit of memory just for these models. And so we ended up with certain customers that just like, well, now I need what, a really big machine, right? If I have large models. And so the server, which traditionally is not a problem in federated learning because the actual work happens in the clients, became the bottleneck. And so in 2.8, we enabled aggregation to disk. And so now the memory consumption is flat, independent of the number of clients. And in fact, it runs faster too, because there's just much less stress on the server, and disks tend to be very fast these days. So I talked about this. So agents are really central to making this more approachable. We optimize across the stack for it. So from the CLIs that make it easy for the agents to use, AutoFL, which the research that leverages these CLIs because it runs them. In 2.9, which we're currently working on, we will provide skills that make the agents even better, easier to use it. So you won't have to, if there was any, even if the 5 lines that Chester showed to use federated learning, even if that's too much, you won't really have to write those anyway, because you can just ask Claude Code or Codex or your favorite coding agent to use it, and it will work. And in future, we expect these agentic workflows that were mentioned before to be happening across the stack. And we will provide the right hooks and capabilities and security points that it's possible to do that securely. I mentioned that already. So I think for us, in general, we provide the core technology on which some of our customers work directly, others work with partners like Rhino. We want to keep progressing the core capabilities with the latest confidential compute capabilities. We'll add in Coco containers soon, but we will keep up with all the confidential compute. We will keep up with the growth in models and optimizing constantly about performance, making the overall thing as efficient as possible. And then provide the right enterprise hooks and features that it's just very easy to work with. So we're just on a constant improvement across, security, scalability, and ease of use in general. I went faster than expected. Perfect, right on time. Questions for Chester and me? Yes.
Yeah, any questions for? Okay.
So we've rapidly moved in securing agentic systems from trying to secure individual agents, individual tool calls, individual MCP kinds of conversation, to securing at the harness controls that confine the interaction between agents and allow you to place guardrails at place where you can use inter-agent context so that things don't happen in untoward ways. But I haven't seen the harness or looping show up anywhere here. Does that fit into your roadmap?
We're looking at where and how the best harness is and who and how to provide it. I mean, there's a variety of them. NVIDIA has several themselves, like OpenShell and others. So we're still looking in how and where that is the best way to do, and which hooks to provide. I don't think for us as an open source, there's not like one perfect solution, or like one solution that fits all needs. We're going to try to provide the right connection points in our stack that that different people can choose. We will provide something that we think is good, but we want to at the same time provide the capabilities for, anybody to do it. We're global. Our products are global. So many different problems happen, different concerns happen across the board around sovereign AI and so on. So we want to be flexible. I don't know. Not an easy answer.
Suggest the ecosystem is looking for NVIDIA to help lead the conversation, not just react to what emerges from individual groups, because that's where fragmentation and balkanization occurs. Right?
Yes.
Let me add a little bit on this topic. So we view there's a two aspect of in the FLARE and the agent type. One is how the agent interact. Take a FLARE as a tool. How I'm a codex or I'm a cloud. How do agent interact with the tool? So that's where the skill comes in. So I can just use a frontier skill agent. I mean, directly using the open source library and say, hey, I don't want to learn your API, just do this for me. And he could do that. I'm sure he can do that without any skills, but he probably making a lot of mistakes, a lot of times and tokens. So one way to do that is adding the specific skills to make this transition more predictable, more reliable, so that's one direction. So basically, FLARE is nothing but another tool for agents. So that's one side. But the other side is the FLARE itself, since it's a federation, itself agentic system. So in other words, the server coordinator could be interact like right now using MCP there. So essentially, the server itself is the agent interact with the customers, taking input in English, and the actuator, in this case, a client on the edge, could be agent. So that's I think some of the audience that was doing the federated query and all the others federated analytics. So those kind of say, what if I ask agent to do the to try to do the analytics for me for the code I didn't write it before. You have these standard federated statistic FLARE already out of box, but what if you do something which we didn't code it before? So whether you can do that. So, or some people say, well, what if I do this data harmonizations, missing data imputations and many other things, so which wasn't pre-programmed. And so that's kind of agentic system. There's a lot of cases I see that there's federated agentic system. So there's when we say there's a agentic workflow that imply both sides. So, but on the second side, if you really say, okay, this is great, I can see these use cases, let's use agent. But I think there'll be not too fast. The reason is, before you have this finite, specifically defined model weight, send it over, you have these, privacy enhancing technology to make sure that nothing leaked out. But with agent, how do you control that? What you can say, well, you cannot send it out. What about we talk about these open shell, the other things, that's on the OS level. What about the application level? I think you mentioned earlier about the agentic ID. So, what can you prove that this agent did what? So there's a whole AI governance and the security have been put on top of it before we basically open the door. So those are kind of things we are constantly debating. Frankly, we have been discussing for a long, long time. And so this I think the world moving in that direction, but we just need to be a little cautious. Put everything quickly. And so that's where we're thinking about it. Okay, other questions?
So in a case that you have a lot of data like distributed across many, like maybe data center, like how does the model like distributed training works, like when the data is not like equally distributed across like different location?
You mean by the data being different or just size?
It could be the data is very different across the sites. It could also be that the amount of data that is being trained on like specific like I assume you're doing like DDP, like it's very different size. Like you are saying like one huge hospital have like 1 million of records, or like a small clinic might have like just like 10,000 or something like that.
Yeah. I think the most simplistic way is weighted average, so that as the weights get back, you weigh the inputs differently. But that's a simplistic way, and there's a variety of algorithms that deal with those particular nuances, depending on, is the data just the same in the same distribution, there's just less, or the data might be totally out of the different distribution. So even if you have a small data set, but it's very different, you might it might be extremely valuable, and you might take that into account. For example, like even these big healthcare institutions, cancer research institutions, say Memorial Sloan Kettering or so on, the typical patient they see there for cancer patients are advanced cancer patients. That's why you go there. You have a really advanced cancer, you will go there. But so their distribution, they might have very valuable data, but it might not be representative of the average cancer patient, for example. So, but there's a lot of nuance in that training and how that works. So that's where all these different algorithms come in play, and all the parameters of them. Yeah, lots of choices.
Any other questions?
Okay, thanks
Okay.
everyone.
Thank you very much. Before I go, I really want to, I forgot at the beginning, but I really want to say thank you for the host, Iris. Yeah, thank you. Thank you for providing a facility for us to be here. So yeah, thank you so much. Hope to see you next time.
Yeah.
97 to 9.
Oh, that's when I got my doctor. Not anymore. This industry.